In question 1, we are given a circle with a centre at the origin and a radius of 1 unit. This circle is called C1, and you are asked to find the equation of the normal to the circle at the point 1 root 3. Please pause the video and try it. Alright, and let's have a look at the solution. We have a circle called C1, which has a centre at the origin and a radius of 1 unit. Let's write down the equation of this circle. C1, and you'll remember from last year, in fact, and perhaps earlier than that, centre at the origin, it's the most basic circle equation you can get. And remember, of course, x squared plus y squared must equal the radius squared, which in this case is 1, so I will leave it like that. We're then told that we have to find the equation of the normal to the circle at a specific point, which is 1 root 3. Well, how do we find the equation of the normal? Well, there's several things we need to do. We know the normal is a straight line that runs perpendicular to the tangent to the curve at this point, so that means that we do need to do some differentiation. And as you look at the equation of the circle here, a preferable strategy would be to use implicit differentiation rather than making y the subject and dealing with a slightly awful looking right hand side. So let's use implicit. So first up, let's differentiate the first term, so that's going to be 2x. Okay, nothing to worry about there, we do it term by term. And then the second term is in terms of y. So when we differentiate, we can apply the rules as normal, but remember, because the variable is y, we have to write dy by dx. And that comes straight out of the chain rule, if you remember from when we did differentiation. So that's dy by dx. And the left-hand side is now differentiated, so we now differentiate the right-hand side, and that's all going to equal 0. Great. Now, let's make dy by dx the subject. So we'll have 2y dy by dx is equal to negative 2x. I've just got to add, beg your pardon, subtract 2x from both sides. And I've just made my x a little bit overzealous there. Great, and we can now divide by 2y, and we'll have a cancellation in the 2 as well. So dy by dx will be equal to negative x over y. So this is the general expression on the right hand side for the gradient at any point on the curve x squared plus y squared equals 1. Which is a circle, of course. Now we're interested in finding the normal. Well, to get the normal at a particular point, first of all, let's sub in the coordinates into the expression for dy by dx. We'll do that up here. So at this particular point, we know that x equals 1. Let's write that in. And y is equal to root 3, and because we know that information, if we substitute it into here, we'll get the gradient at that point of the curve. So dy by dx so x is 1, so that's going to be negative 1 over root 3. So the gradient at that particular point is negative 1 over root 3. You could be tempted to rationalise this, but there's no need, because we're going to find the gradient of the normal now. Now remember that the normal is perpendicular to the tangent. I'll just sketch this to remind you. So remember that if you have, let's say this is the tangent, so we've got a straight line like that, and it has a gradient of m. then the normal will be any line that is perpendicular to the first straight line, and that will have a gradient of -1/m. And consequently, if you multiply both gradients together, you get -1. Now notice, of course, that the gradient of the normal is the negative reciprocal of m. So we have to find the negative reciprocal of this. I'm going to use some notation here. If you, I don't know if you've seen this before, but if you want to say that you're writing down the gradient of a normal, you can use this perpendicular symbol. I'll just do it now. So it's like an upside down T. It just means that the perpendicular gradient at that point. So m perp is going to be the negative reciprocal of this, and that's just going to be √3, which is much nicer. Because if you multiply both of these together, you will get -1, which is part of the definition. Great. So we have the gradient of our normal, which is good news. What we need now is to calculate, or not calculate, but we need to find the equation of the normal. And we have our coordinates, so we just substitute everything into the formula for the straight line. So y minus the y coordinate which is √3, must equal the gradient, which is √3, multiplied by x subtract the x coordinate, which is 1. Now then, let's expand this. You're not actually asked to give the equation in a particular way, so there wouldn't be anything wrong with this answer, but there's something I'd like to do which will lead into part B of this question. Let's just expand it. So y subtract √3, and that's going to give us √3x subtract √3. Now notice here that we have -√3 on both sides of the equation. That means they're going to cancel, or we can add √3 to both sides. So that's going to go, and so is that, which means we are left with this as the equation of the normal. So our final answer is going to be y is equal to √3x. And if you think about it, of course, this is a straight line with a y-intercept. Well, it's not missing. Its y-intercept, of course, is 0, isn't it? So that means it passes through the origin. And in part B, we're going to show that this is true for any normal to a circle such as this. Next, you are asked to make a generalization based on what you found in part A, in that the normal to C1, which is the circle, at any point on the curve will always pass through the origin. Please pause the video and try it. Okay, and let's have a look at the solution. Next, we're going to make a more general deduction. I've put the curve C1 back on here again, and the gradient that we found in part A, which was -x/y, and I've also included a diagram to show you the intuition behind what we're going to do. As you remember, we found that the gradient of the normal actually passed through the origin, and I've drawn two tangents in green to the circle here. This could be any circle really, as long as the centre is at the origin, and I've also added two normals to each of the tangents separately, and as you can see, it looks as though these normals are going to pass through the origin no matter which point I choose on the circumference. Now if I want to just generalize any point on the circumference, what I can do is just call it something, and one of the most general ways of doing it, and well, the standard way to do it, is to choose any point x0, y0. So I'll add that to the diagram. So this could be, for instance, the point x0, y naught. The subscript is just to make it distinct from the variable x and the variable y. And same with that, so that it just represents any point. If we want to find the gradient at any point on the curve, on the curve C1, then we would sub in x naught and y naught, and that would fix it, it would make it constant. Now, to find the equation of the normal, I simply reciprocate this, but I'm going to sub in the coordinates first. So let's do this. So at x naught, y naught, like that, with brackets around, of course, we have dy by dx would equal negative x naught over y naught, a constant. So this means, of course, that the normal is going to be the negative reciprocal of that. So therefore, and I'll use the same notation as previously, the perpendicular gradient, if you like. Remember, this is also m. Let me just make that clear. This is equal to m, of course. So equals m, the gradient. The perpendicular gradient will be the negative reciprocal of that, which would be y naught over x naught. All right. So now we have that. In a similar vein to what we did in part A, we're going to form an equation of the normal. So we've got the gradient of the normal there. Now we just sub everything in. I'll just move over here. So let's use the formula again. So y minus the y coordinate is going to equal the gradient. So that's the perpendicular gradient multiplied by x, subtract x naught, like that. Right, okay. Remember, the perpendicular gradient is y naught over x naught, so we'll put that in. This is as general as you can make it, really. X subtract x naught there, like that. Now then, let's multiply this out. So this will give us y minus y naught is equal to y naught x over x naught, subtract y naught over x naught multiplied by x naught. Now the x naughts will cancel, of course, so that you're just going to be left with y naught. And this is the kicker, isn't it? So remember, we had negative root 3 on both sides. So we would have got that no matter which point we had chosen. And the negative y naughts will, of course, cancel because I can just add y naught to both sides. So this is gone and this is gone. So any equation of the normal which has to a circle with the centre at the origin is going to have this form. So we have just shown, and I'll just finish this off, the equation is going to be of the form y naught over x naught x, and just if you want to make it absolutely clear, remember this has got a y-intercept at the origin. All right, now this is a natural thing to do. If you want to study mathematics, of course, you answer the questions, but then you can follow up with more questions and more deductions. Can you generalize the result? What other questions arise? Things like that. So always be thinking about what are the implications of what I've just found. Is there more to it than just what I found, or is there more to it than just what's on the surface? In question 2, you're asked to write x over x plus 1 all squared as partial fractions. Please pause the video and have a go at this. Alright, and let's have a look at the solution. Next, we have to write x over x plus 1 all squared as partial fractions. Now, I've included the scaffolding here that you weren't given in the question. This is just harking back to when you did the work on partial fractions. So remember, you're going to need a linear term in the denominator for the first partial fraction to acknowledge that it's x plus 1 as a factor, and you also need to have x plus 1 all squared, because you have two identical linear factors multiplied together. You cannot write a over x plus 1 plus b over x plus 1, because you might as well just write a constant over x plus 1, and that will not factor in the x plus 1 all squared, and that's acknowledged over here. So you've tried and tested that approach and saw that it doesn't work, so this is the way to go. Okay, so let's work on the right hand side and recombine what we've got here to create the left hand side. So working on the right hand side, we're going to get this. So everything is going to be over x plus 1 all squared. Let's get that in there. Okay, and let's think about how do we form the equivalent fractions. Well, we're going to need a on top, obviously, and to create a over x plus beg your pardon, x plus 1 squared in the denominator, clearly we must multiply a by x plus 1 to make sure it's an equivalent fraction. So that's a lots of x plus 1, and then nothing happens to the second fraction because it's already over x plus 1 squared, and all that must be identical to x over x plus 1 squared. So we can now dispense with the denominator, that's not necessary. So we can create a new identity just in terms of the numerators. So we're going to have ax plus a plus b must be identical to x. And it's completely up to you how you want to do this. We can equate coefficients, or you can make a substitution. I think I will equate coefficients. So let's look at the x's first. So for the x's, alright, so we've got a lots of x on the left equals 1. So a we have straight away. And let's look at the constants now. So for the constants, I'll use C for that one. I've used C before. Constants. And we've got a plus b equals 0. And no constant is 0 on the right hand side. And because a is 1, the implication, of course, now I'll just sub it in fact, so 1 plus b equals 0, so that means that b equals -1. So there we have our a and b, and it's good practice, of course, to write the final answer properly. So we have x over x plus 1 all squared is absolutely identical to 1 over x plus 1 subtract 1 over x plus 1 all squared. There we have it. In question 3, we're going to use the partial fractions from question 2 to evaluate a definite integral, and we're asked to give it in a particular form involving natural log. So please pause the video and try it. Okay, and let's have a look at the solution. Now we have our partial fractions, we can use our result to complete an integration. And what we're asked to do is to integrate between 0 and 1 x over x plus 1 all squared. Now, because I have the partial fractions, I can rewrite the integral like so. From 0 to 1 of x over x plus 1 squared dx must be the same as, because we've just found an identity, of course, the integral from 0 to 1 of 1 over x plus 1. Now what I'm going to do is I'm going to split the integrals up, because we've used this in previous lessons and it will just save time in the working out. So I've got 1 over x plus 1, and then that's going to be integrated with respect to x, so that's dx, like that. And then subtract the integral from 0 to 1 of 1 over x plus 1 all squared dx. Great. So that's how we're using the partial fractions. Now let's have a look at each case separately. So I'm going to call the first one integral 1, and the second one integral 2. So this is going to be referred to as integral 1, and this is going to be integral 2. Alright, now integral 1 is pretty easy. It's just a derivative over a function. It's the log function. So I don't have anything to worry about here. I can just write down what the answer is. So for integral 1, let's write it at the side over here so show it's been done. So integral 1 is just going to equal natural log of the modulus of x plus 1. Okay, I'm just doing that as an aside for now, just while we complete the integration process. Integral 2 is slightly different. So for integral 2, we don't have a derivative over a function, so it fails that test. So I'm going to use a u substitution here, and we're going to have u. So let u equal x plus 1. Alright, now du by dx, this is where you get the nice result here. Du by dx is just going to be 1. So I can interchange my u and my x without having to worry about any cancellation or anything like that. It's just going to pull the x plus 1 straight out. So therefore my du is equal to dx, like that. Now this means, of course, that my answer, I'm just going to partition what we've got. So let's just put a box around this, like so. So I'm just continuing with the question now. So we now have the results for the first integral, integral 1. So that's going to be the natural log of x plus 1 between 0 and 1. That's done. And then we still have to do the integral in the integration for the second integral. So we're going to integrate from 0 to 1, 1 over u squared du. And remember, because we have the limits in there, these are x limits, not u limits. You can change them to u limits if you like, but these are x limits at the moment, so they're equal to x values. Now then, so I've got essentially u to the power minus 2. Now if I integrate that, u to the minus 2, let's do this over it. So remember, that's essentially what I have here. If I integrate, I add 1 to the power and divide by the new power, so that's going to give me minus u to the minus 1. So if I add 1 to the power, that's minus 1, divide by minus 1, it just makes everything negative. Okay, and then I can put my x plus 1 back in. So that's just saved a bit of time there. Right, so let's do the next step. So that's going to equal the natural log of x plus 1, close the modulus from 0 to 1, and then I'm going to subtract minus x plus 1 to the power minus 1, evaluated also between 0 and 1. So just do a bit of tidying up with some of these indices here. This is going to be the integral of ln of x plus 1 between 0 and 1. And then I've got a double negative there. I can add that now. So that's going to be plus 1 over x plus 1. And this is being evaluated between 0 and 1 also. I mean, what you could do as well, you could combine both of these if you wanted to, but we don't need to do that either. Right, okay, let's put the numbers in. We're nearly there. So this is going to equal, well, I've got the upper limit of 1 here. If I put that into this expression here, I'm going to get ln of 2. So that's ln of 2. Subtract ln of 0 plus 1, so that's ln of 1, which is of course 0. But I'll write it in anyway. Alright, and then I've got substitute in 1, so that's going to be 1 over 2. And then 1 over 0 plus 1, which is 1 over 1, which is 1, of course. So that's subtracted. And I'll just make it distinct because these are our upper and lower limits substituted in. So this is going to essentially have brackets around it, and so will this. And I'm just conscious of space here, so I'll just write the final answer now. So as we've said, natural log of 1 is 0, so my final answer is going to be ln of 2. And then I've got plus a half subtract 1, so that'll be subtract 1/2. And this is in the form log of a plus b, which is what it required in the question. Lastly, in question 4, we have a Cartesian curve C2, where x is the subject, and it's defined between negative pi over 4 and pi over 4, not inclusive. And we have to show that the gradient dy by dx is the expression given on the right hand side, all in terms of x. So please pause the video and try it. Alright, and let's have a look at the solution. Alright, so the last question for today, we have a function, a curve defined in this particular way. So x equals 3 sine of 2y, and so x is the subject. The range of values of y are from negative pi over 4 to pi over 4. So our task is to find or to show the derivative can be written in this particular form. This is a very popular type of question that's come up on the new specification, and it's worth getting good at these types of questions, and you can set them up yourself if you like as well. Right, so let's differentiate. Now, it's not strictly implicit differentiation. This came up a lot earlier in the course, earlier in the differentiation chapter. You can find a derivative, dy by dx, simply by finding dx by dy and then reciprocating. So we can do that initially because then we know we've actually got the derivative written down and it won't take too much effort. So dx by dy, and remember this makes y the independent variable, so I don't have to use dy by dx on the right hand side or anything like that. We just take y as the independent variable and x as the dependent variable, as you can see here. Alright, so if we differentiate sine, of course, sine of 2y, which we have here, this is going to give us 2 cos 2y, and because I've got the 3 at the front, this is going to be 3 lots of 2 cos 2y, so that's going to be 6 cos 2y. It's a standard result, really. Bit of chain rule perhaps, but pretty much a standard result. Alright, now if you look at that, then you'll think, well, okay, I've got dx by dy, I want dy by dx, let's reciprocate both sides of the equation. So dy by dx is going to equal 1 over 6 cos 2y. And this is where your skills are tested, because you'll get that and you'll think, well, this doesn't look anything like what I'm supposed to get. Have I done something wrong? Well, the answer is, of course, no. And the key thing here is to notice that all of this on the right hand side is in terms of y, and that's the problem. All right, we don't want that. We want everything in terms of x. So what do we know? Well, the cos of 2y needs to come out of this somehow. There's no trig function whatsoever in our final expression. What do I know? Well, we do want x. We don't want y, and we don't want trig functions. Now, we do know that x can be written as 3 sine of 2y. Let's work on that. How are cos of 2y and sine of 2y linked? That's what you should be thinking. Well, if x, I'm just going to write this up here, equals 3 sine of 2y, then let's make sine of 2y the subject. Therefore, x over 3 must equal sine of 2y. And this is where the second piece of kind of misleading information creeps in, because when you see the 2y, you'll be thinking double angle identities, and perhaps when you see that, this won't do you any good here, because we want to remove any sign of any trig function whatsoever. We can do this because we know that cos and sine are inextricably linked. So cos squared 2y plus sine squared 2y must equal 1. It doesn't matter that it's 2y. We can call this angle anything we like, but we have to be clear that we have to get rid of these trig functions. It's absolutely essential that you notice that. So what do we know? Well, let's write it down. So we know so if I have sine squared, I'm going to put theta in here first, plus cos squared theta, just some angle, is absolutely identical to 1. But so what? It's theta. Let's call it something else. So let's call it the thing we're interested in this question, which is 2y. Just be consistent with your angle. So this is actually 2y. Or it could be anything you like. It depends what the question suggests, of course. So that's also valid. Now this means that I'm actually onto something, because I know sine of 2y is x over 3. So I can replace this with x over 3 squared. So that's going to be x over 3 all squared. Plus cos squared y is equal to 1. I'm dropping the identity now because we've substituted in a specific expression. So this means, of course, let's just rearrange a little bit more. Cos squared of 2y must be equal to 1 subtract x squared over 9. So that means cos 2y must equal the square root of all that. Now then, how does this help us? Well, let's have a look at our expression again. I can now replace the cos 2y here with all this. So this is going to equal 1 over 6 lots of the square root of 1 minus x squared over 9. So it looks like we're onto something, and perhaps we're close to a resolution here. Now, we don't want x squared over 9. So I've got to think of a way of removing the divisor 9 in this expression. How can I do that? Well, let's just have a look at this expression a bit more closely. So I'm just going to take this bit here and just do another aside over on the right here. Okay, so let's write it out. So we have 1 subtract x squared over 9. And wouldn't it be great if I could clear the 9 from the denominator? Well, let's do it. If I times all of this by 9, I'm going to get 9 subtract x squared. And that solves that problem, doesn't it? But what I've done is I've changed the answer. I've multiplied everything by 9. I'm not allowed to do that really, because I'm changing what I've actually got over here. This is the same problem that crops up when we do log questions. So I can compensate for what I've just done, and I can make it equal by putting 1 over 9 at the front. Now nothing has changed, but I don't have x squared over 9 here anymore. Now let's see how that plays out over in the expression here. So let's write it out again. So this is going to equal 1 over 6 lots of. Now what I'm going to do as well is, because I have 1 over 9 written here, what would happen if I took the square root of all this? Well, let's do that. Oops, my square root's gone right through my 2, never mind. I've got to square root all this as well. And square rooting the whole expression here means I square root each factor here. And 1 over 9 has a rather nice root. I can write it as follows. So it's going to be 1 over 3 multiplied by the square root of 9 subtract x squared. So I can now say, well, all of this here I can just replace with 1/3 of the square root of 9 minus x squared. So let's put that in. Sorry, 9 minus x squared. So all that can go in place of the square root of 1 subtract x squared over 9, because we've just shown that they are identical statements. And just to tidy up, we have a final answer, so that's going to be 6 multiplied by a third, which is 2, so it's 1 over 2 multiplying the square root of 9 subtract x squared, and we have it in the form required.